I realized today that it's probably the first time that I'm the oldest person in the audience, in the room, although there might be other people listening that are older than me. So I think it's appropriate that I give some perspective of where we are coming from and where we should go. So this is going to be more an historical and political talk, and I'm not going to be so focused on the current development. So I want to start. Let me see if I can get page down working here. This one is super. Oh no, now it's moving. Don't worry, Anwar, there is a map of South America here, but I'm not going to speak about soccer. So I did my PhD down there in Patagonia, and for reasons long to explain, we had this reproduced down there the experiments of superconductivity, and that was good enough to get money to do more experiments and buy a computer. And that was the computer where I did my thesis. It had a amazing 16 megabytes of memories, and it's running 5 megahertz. Of course, that computer was not powerful enough to run DFT calculations in real materials. So I could only do DFT calculations in models at the time. However, I just want you to look at the number. It was 120K. In nowadays dollars, it would be a little bit over $300K. So that computer was about 1 million times less capable than my old iPhone. I have one better now. If one consider both the memory and the increment speed, phones today are easily 1 million times larger. And imagine you couldn't take a selfie with that computer. It didn't even have a camera. Only an internet connection at the time. So let me mention now Titan for a moment, not the most recent computers that we have, because I'm going to use it as a reference. Of course, the Titan is 10 to the 16 times larger than that old computer today. So it's even completely different qualitative comparison. There are lots of things that can be done in Titan. And that's one of the reasons I moved to do QMC after doing DFT, better computers. So we did some numbers with Jaron recently to buy a new cluster for the theory efforts in ORANL, a local cluster. And when you add up, basically with a little bit less than this 300,000 K, you can buy a cluster that, if you take into account the number of cores, hyper-threading, number of days of a year, the 24 hours, it gets to 50 million hours. That is about 2% of what it was Titan. And that is within the budget that even a small institution at the end of the world could have to do computations. And that I want to tell you that this has happened before. there was a time where the small institutions around the world have enough funding to do DFT calculations that were forbidden before. And that was when DFT took off as the dominant method for calculations in real materials. And nowadays, we are crossing that point. So that is why I think that this is the moment for this kind of methods, and why you have to enter the field and not leave the field. And you have a future in this area. So what kind of science can we do with 2% of Titan? Basically, for yourself, in your own institution, you potentially could buy a cluster of that capability. You will run it differently, but you will not have the same time to solution than with a machine that is massively parallel. But in principle, the calculations could be done within the year. So what Titan allows us to do is to move from simple systems that could be done by DFT to highly correlated materials that included semi-core electrons and were too difficult to handle before. And what I'm going to do is to show you some examples of what we could do with Titan, and that would be an example of what kind of calculations can be done everywhere in the world nowadays within a reasonable cost, not an impossible cost. So all these calculations that I'm going to show were primarily done with a minimal DMC approach. We were using important sampling, just as late adjuster, and a single determinant in most of the cases. And we were using DFT nodes, and most of the calculations were done optimizing the nodes, but just varying one parameter, the U parameter. So this is what I'm going to show here, about 80 atoms, and from 500 to 1,000 electrons were the typical calculations that I'm going to show. With that approach, we could show that we were generally better than DFT, and that the remaining errors can be corrected, and people will show work on progress in this workshop on how these errors are being corrected. We have done a small contribution in that direction as well. So when I was in Livermore, I joined a team that had Andrew Williamson, Jeff Grossman, and Randy Hood. And that's how I became acquainted with DMC methods. And I was very surprised that they could do a calculation on a silicon cluster of 200 atoms that I could only do 5 years before with empirical pseudo-potentials. So that caught my attention because I saw the potential of the field. I was working in DFT at the time, but I joined the discussions over on the lunch table. That's why I learned. When I was by my 5 years, I decided to apply for a grant, a lab-wide grant in Livermore to do a DMC calculation on aluminum of the bulk equation states and defects. And that's probably something that you will have to do. You will have to find support in some way to do your own program. The reasons I chose aluminum wasn't because it was particularly fancy, but Livermore had interest in the material, and in particular interest at high pressure. So that's why I got the money to do that research. But things happened, and I ended moving to ORNL where I am now. So Randy Hood took over the project. And that was a lucky event because Randy Hood had done his thesis on QMC developing a casino. And a casino also because of my connection to Andrew Williamson, Randy, and also Paul, was the first code that I tried. So the results that I'm showing here are casino, no QMCPACK, and were obtained by Randy Hood, and were very accurate equations state that solve even small errors of LDA and PVE. So Randy went over and did the calculations of the effects that I had proposed and obtained formation energies of vacancies, interstitials, and comparing very well with the experiment at the time. So these were calculations that included thousands of electrons and were using supercomputers in Livermore. I'm not sure I can tell the names. Nowadays, some of them were behind the fence. As I said, the agreement with the available experiments were very good, improving even small errors of DFT. So, although these calculations and these results were not striking because this is a system that is too easy, DFT works well, we could correct a small error. And it was important to get some traction because this allowed me to be brave and be able to present this as a plan to DOE. And we could convince DOE to have a DMC program. And so that's how we tried to hire first Lucas, who was developing QWalk. And we also were more successful with Paul when I became PI of a grant to hire Yonin Kim. And that's how the code QMCPACK that was developed here in Illinois, in Urbana, moved with Yonin to being developed in Oak Ridge, at least in part. But the big reason why we stopped using Casino was that QMCPACK and QWalk were open source and we could see and modify the code. So QMCPACK became a community code, and we were infected essentially in Livermore and from the QMCPACK environment. So this is a reason why we are doing QMC calculations. Instead of DFT, is the difficulty of DFT approaches to solve the self-interaction error that typically occurs when you have orbitals that have very different degrees of localization in the material. That's why we have problems in transition metal oxides when you have a partial field shell with d electrons and s orbitals and other orbitals of different atoms. So that gives a problem of the alignments of these energy levels. And that's one of the reasons there are big errors in transition metal oxides. They are called highly correlated, but they are self-interaction errors. It's not really the correlation error. There is a correlation error that appears in highly inhomogeneous densities And that is well known from this relatively old work from Nevoki, Forbes, and Needs, that they did studies in a highly homogeneous electron gas and shown that the exchange correlation hole is similar to DFT common approximations at the high density regions, but is extremely different at the low density regions. And that gives rise to the correlation error. To be fair, DFT approximations have become slowly better over time, and people have been improving the exchange contribution in the functionals with the hybrids and functionals like scan, but still there are problems that are very difficult to resolve. And this paper here that I'm showing was one of the reasons that I would start thinking it's more difficult to do DFT and solve the problem than do directly the many-body calculations in QMC. So I'd like to give credit to that paper. So when your name move to ORANL, we will able to build QMC effort, but DOE requested me kindly that I shouldn't do easy systems, and they asked us to do highly correlated oxides that were a class of materials that I was extremely scared of. So I'm thankful for the encouragement of DOE. Otherwise, I would have stayed away from this mess. So the first problems that we had were the design of pseudopotentials. And that's something that we have been working, and also several people in this room have been working in obtaining better pseudopotential for transition metal oxides. But the first pseudopotentials that Jaron and Juan Santana obtained allow us to do the first transition metal oxide calculations. Here I'm showing results from Juan on the equations state of a ferrite. And he also continued the study for the effects where there were bigger errors on DFT. So, for example, here we show the results of DFT compared to experiment, that is this band here in the middle. And DFT approximations are all over the place. The DMC calculations are almost overlapped within the error bar and experiment. The results from the lanthanum ferrite are less convincing because the error bar is so big that any theory is inside. So I have to check now if there is any recent experiment that help us decide which one gets it. But the calculations from Juan show in part what was the reason of the disagreement. Here what I'm showing in the figures in the upper left corner is the density that results from two differences of densities of adding an electron or removing an electron to the system. So the density in red is the density of the last electron added to the system, and it's integrated on the plane and plotted in the z direction. So the upper figure is for the perfect material, and the result shows that there is density is much more localized for the DMC calculation than from the DFTs. And as I was saying, that is mainly due to the self-interaction error that simple density functionals fail to correct. The result below is the same, but for an oxygen vacancy in the ferrite. And when you see at the center of the graph, that's where the vacancy is placed, you find large differences in that density of the last electron in the system. And the plot on the left is from an isosurface. And you see that this block here in the center is where most of the change in the density occur. And that's why you have such a big difference in formation energies from different theories in DFT. So an accurate description of the exchange in the is very important for the defects. And it's a lion's share of the error that DFT has to correct to get a better answer. So these are another results in the case of cobaltites that we had some benchmark data coming. This is cobalt monoxide, I'm sorry, that could be used to benchmark how good was the method. And at the time we were doing these calculations, we were focusing on materials where we had an experimental validation because we have to establish the technique as a reliable tool to do complicated materials. So for the cases that we have experimental information available, the DMC calculations were significantly better, overlapping with the calorimetry measurements that we have. In some cases, the DFT approximations were qualitatively wrong, producing the opposite sign of what experiments suggested from the stability of these three phases, the zinc blend, the rock salt, and the versite. These are difference between the structures compared between the different methods. These results were obtained by Callahan Saritas. Also, we have similar agreement for the bulk moduli, although in this case, DFT does a reasonable job, or the error is larger in the case of the lattice parameters. We did also with Callahan an effort to do calculations of excitation energies for substitutional magnesium in different oxides. This system, you have a defect on a crystalline field that is octahedral and splits the d orbital into a triplet that is T2G and a doublet in higher energy that is the T2G, the EG. This is very common in the perovskite materials and in other classes of materials where you have octahedral fields. And the excitations that we were able to calculate is moving and flipping one spin or promoting an electron from this state to the EG. And the results from the energy difference of these two ground states for different occupations from the spin show very good agreement with available experimental data. Here is in green the experiment and our DMC results. So for the cases where we could find experimental information available, the agreement was very good. It's known that the EFT in general gives smaller energies for the excitations. There are cases, however, where QMC doesn't work so good with this simple approach. For the first case that we found where we had problems were for the excitations of some of monoxides, like cobalt oxide, our nickel oxide. The excitations are much larger. The gap is much larger than what is measured in experiment. So that is probably related to the same problem occurring in lithium cobalt dioxide. Your study, Kevin and Anwar, showed that the orbital where the electron goes is quite different from the one that we get from the FT. And therefore we have to do better than these single determinant calculations that we are doing starting from the FT to correct for these excitation energies. So you probably would like to try with this material as well and see if the error is corrected. Of course, we were not the only ones working. Also, other people like Sandro Sorella, Andrea, and other Lucas Wagner here in the States were working in similar materials. That and among all the community, we have been able to show that these calculations are practical with the supercomputers of the time, but now are becoming accessible, as I said, for a large number of people in the world. So here there are some references of other work. This is not comprehensive. This is just about the work was done in the 2010s. And there was a review written at that time by Lucas and also that was roughly the status of the field at the time. And I think that is essentially describe what can be done with 300K of budget for the computer. Also with Titan, we were able to go beyond single solids and do some calculations on simple nanostructures, super lattices. So Callahan Saritas already as a professor, we have a collaboration with him, and he studied the formation energies of an oxygen vacancy on a super lattices of two highly correlated materials, of two ferrites. You see here that there is a large variation on the formation energy at different sites in the super lattice. And sometimes they give completely different qualitative results. Some theories describe that this V1 position here is a lower energy, but other approximations choose a different position on a different oxide from the vacancy. So Juan was able to calculate the formation energy barriers, formation energies, and also the migration energy barriers. And this has been long known from results in molecules that usually the FT gives a much worse behavior for transition energy barriers between two minimum. The same happens in solids. So this would be important for battery materials and what else. So this is another result for a superlattice of a lanthanum plane inside a strontium titanide. This is something that was also done by Juan Santana. And I want to share you to pay attention to this lower part of the graph, where it shows the localization error again. The DMC calculations have a much larger modulation of the electronic charge of that last electron than DFT. So I'm going to skip these results on lanthanum cobaltite to give you a short message in the interest of time. This is a very complicated material because different configurations of the occupations of this multiplet compete with the same energy. So that makes the standard simple approach in that we have used in DMC have difficulties, and we have to use probably some multi-reference here, and probably relativistic effects are important in this scale. So this is still work in progress. Not every material can be handled with this approximation, and I think this one is one of the cases. But anyway, we could did some calculation in this case, also Callahan. But in the interest of time, I'm going to jump into new things that we are doing. This is a collaboration that we have with JAIS in Japan that is also using QMCPACK over there for calculations of effects. So let me describe a little in the remaining time some of the things that we are doing for the near future. We kind of rediscover the pseudo-Hamiltonian approach. That is a modification on the pseudo-potential approach that instead of only modifying the potential, we can modify the kinetic energy. This was not invented by us. A number of people worked on this 15 to 20 years ago, and it was abandoned because it was believed to be impossible. The reason it's now impossible is because we are including the semi-core electrons. So that allows us to construct the pseudo-Hamiltonians even for transition metal oxides. So we are also reintroducing the self-healing algorithms, and there are new methods to calculate the excitations that we are testing now and trying. The work on pseudo-Hamiltonian, we starting with Jaron doing hybrid approaches where we could have a mixture between something that was a pseudo-Hamiltonian with the non-local part condensed in a much smaller magnitude. Then with Chandler, who developed abilities to do very accurate ECPs with Lugos, we asked him to help us to do a pseudo-Hamiltonian for the case of cobalt, and he was successful. And later Tomohiro learned from Chandler how to do pseudo-Hamiltonians. And we have from half of the internal transition metal oxides. And we think that this will largely remove one of the source of errors, that is the locality approximation that Andrea was describing in the previous talk. It's a different approach. Essentially, we can modify the kinetic energy, so the pseudo potential is now local, so we don't have locality error. And that entails modifying the DMC algorithm. And Jaron did the modifications at the level of the CPU code. This is still not running at the GPU version, as I'm aware. The other method is to calculate the excitations. This has been tested only in very simple modes, but now we are trying to modify and hack PyQMC, the code developed by Lukas Wagner, to try to test this method in ab initio systems. So this is a short result that shows that at least we can calculate the auxiliary bosons we haven't calculated yet the observable that allows us to get the excitation corrections. Finally, we are resurrecting the self-healing algorithm that we were testing and proved ab initio 15 years ago with Michael. How long ago was it? So we developed this with Paul and Randy and in models, and Michael helped me to do calculations modifying QWalk. I was still running Casino at the time. So this is a relatively simple approach. When you do fixed node calculation, you find the ground state of all the wave functions that share the node of a given trial. So the wave function is only different from an eigenstate at the node. Okay. That's why if you don't provide the right nodes, the wave function has to have a kink at that point. If you smooth that kink, it can be shown that the node moves into the correct direction and you have a better wave function for a trial as before. So we show that this method works for relatively large systems. At the time, this is a calculation run in Casino. This is a C20. And so we have roughly force 2080 electrons. But for the time, it was a good achievement. We think that we can do this for a real solid, and we are working with Anwar to try to do it these days. So Jaron has resurrected the self-healing algorithm and installed it in QMCPACK, at least a simple version of it. And Nicole Spaneda, a recent postdoc that just joined our effort, is testing it. So hopefully this will become available. So to conclude, because I'm running out of time, I hope I'm able to show that we are at the point where anyone in the world will be able to do the calculations that were possible in the supercomputers in national labs only 13 years ago. So that may help you to make a decision to learn DMC method and continue in the field, because I think it's going to expand very soon. With that, I let you ask any question if you want.
Thanks very much, Fernando. So I'll see if there's a question in the room, and then we'll go to online. So if you're online, either put a note in the chat or get ready to unmute. Anything in the room? All right, I'm going to ask you. Go.
Thanks for the talk. So when you show the calculations, any calculation that show the defect calculation, how do you optimize the structure around the defect? Do you use TMC or DFT?
Yeah, that's a good question. For most of those calculations, we rely on DFT to give us the position of the atoms. It's generally believed that DFT doesn't do that bad job for the positions of the atoms. And we have tested different geometries around the minimum and trying different density functionals to see if there was a significant error. So at the time, we didn't have tools to do relaxations of forces for such large systems. The method that Jaron has developed, and he will explain tomorrow, allows some optimization using a mixture between DFT and the DMC approaches. But in some cases, we started with ideal structures, just removing an atom and keeping the rest of the atoms in the bulk position because it was easier to describe and use it as a benchmark. So it's independent of the approach. In general, we relax the forces with DFT. In the systems that we tried, the impact was small. And basically, we are in the regime where the system is parabolic. So if you are not that far from the minimum, you are not making a big mistake.
Thanks very much. Anyone online? I don't see anything in the chat, but if you want to ask, just unmute, go ahead. And I'm going to look around to see if there's any other questions.
Mika promised me to make a hard question. Yes.
See if there's anyone online first. All right, Mikhail gets the question.
So hi there, Fernando. It's Michael Badic, Slag National Battery. So do you think self-healing algorithm can potentially relax this delocalized electron to localized electron in metal oxides?
Yeah, I think it could. The question is whether there is a faster method than self-healing DMC. In some cases, we have, in particular in quantum materials, we have a highly degenerate space of excitations that have similar energy, but produce wave functions with a very different shape. That's the case where I see a self-healing have an area of application that competes with advantages with other methods. But for the system that you described, I would favor, without knowing much, the approach that Kevin and Noah have been developing. That starts from a highly correlated wave function. Also, perhaps for systems that have such a big gap in energies, energy minimizations approach may be more advantage. Is another method that has a different regime where it is advantageous that when the energy dominates, I wouldn't choose it, although it will converge. As I said, computer time is becoming less expensive than human time. So self-healing is very robust and could save you human time. So in the future, having the certain method may be more advantageous because the computer time certainly becoming less expensive.